All right, hey everybody, back here for Chapter 1, Lesson D, as in Delta, Part 2, Parent Functions, and now we're going to dive into some non-rigid transformations. Therefore, our graphs will not have the original shape that they did. We're going to distort them in some ways by stretching and shrinking them. So we'll review the 8 parent functions, and then we'll get into some of this non-rigid transformation stuff. So let's get started. Okay, just a reminder of the parent functions that we talked about in the last lesson. This is not the extent of the parent functions. This is just those that we will be working with for the time being, but we will see many, many more, and we'll be performing transformations on many of them. If you have any questions about the greatest integer function, please contact me and we can talk through that, maybe in a Google Meet or something to that extent. So please make sure that you're aware of each of these parent functions as we move forward. Okay, so here we have got the definition of a non-rigid transformation, which is a transformation that distorts the parent function or otherwise, possibly not one of these parent functions, maybe a generic function, by stretching it or shrinking it. And there are 2 types of non-rigid transformations, vertical and horizontal stretches, as well as vertical and horizontal shrinks. We've got a number of graphs that I'd like to go over on the next slide. But in preparation for our first test, this will be our last lesson prior to our first test. So please make sure and attempt the quizzes that I've got available for you. Those are very good practice for preparing for this test, as well as the review materials, which I will have posted in between lessons. Delta is in D and echo is in E. So pay attention to those, and then again, feel free to shoot me a message if you've got a question. So let's get into some of these non-rigid transformations. Okay, so vertical and horizontal stretches or shrinks. I have a mistake on my slide here. This is not considered a translation. Stretches and shrinks are not translations. Translations are shifts up and down, left and right. So let's read the following so that we can understand vertical stretch, shrink, and horizontal stretch and shrink. So let C be a positive real number. Stretches and shrinks of the function y equals f of x are as follows. They'll follow these rules. Vertical stretch by a factor of c if c is greater than 1. So if we multiply f of x by a number greater than 1, for example, h of x below, okay, that's going to be a vertical stretch by a factor, in h of x's case, by a factor of 2. Okay, a vertical shrink by a factor of c if c is between 0 and 1. Would be a vertical shrink. So g of x below represents a vertical shrink. So we're going to squash that graph vertically, whereas h of x, we're going to stretch it out vertically. Okay, t of x would represent a horizontal stretch. So in this case, c for t of x is 1/3. So you can see in rule number 3, a horizontal stretch by a factor of c is if c inside the function, again, horizontal transformations happen inside the function. Okay, if that value is between 0 and 1, we will have a stretch. So that you can think of it as stretching the function horizontally, pulling it, kind of like a rubber band. Okay, and then for number 4, horizontal shrink by a factor of c. If c is greater than 1, it's going to squish that graph toward the y-axis. So we're going to do that with m of x. It looks like we're going to horizontally shrink that by a factor of 1/2. Whereas t of x, we're going to horizontally stretch that by a factor of 3. Okay, so let's take a look at h of x. We're going to stretch this by a factor of 2. So all I'm going to do is take my f of x values and multiply them by 2. So f of x here is 0. So it's not going to change if I multiply it by 2. F of x here is 1. If I multiply that by 2, I get 2. F of x here is 2. If I multiply that by 2, I get 4. And likewise on the other side, positive 1 multiplied by 2 is 2, and positive 2 multiplied by 2 is 4. I'm just stretching that graph of h of x vertically I just knocked my iPad over. That's probably what you heard. But there is a vertical stretch by a factor of 2. So what if we vertically shrink this function in g of x's case? That would mean I would take all of the points of f of x and multiply them by 1/2. So there's a 1. Let's go up here to a 4. Here's an output of 1, and here's an output of 4. If I shrink it, that means I would take each of these points and multiply it by 1/2. So 1 becomes 1/2, 4 becomes 2, 0 will stay 0 when you multiply it by 1/2, and I have now, I like to think of it as kind of compressing that graph down toward the x-axis. That would be g of x, which would be 1/2 f of x. Now let's define h of x. H of x here would be 2 absolute value of x. That's what it would look like without f of x's actual notation involved. Likewise, g of x would equal 1/2 of x squared, or x squared over 2. Awesome. So the green graph would be g of x, which is x squared over 2. The red graph would be 2 times the absolute value of x, which is h of x. Let's look at some horizontal stretches and shrinks here. Okay, so if I were to stretch t of x horizontally, that would take every point that I can at least see clearly on the graph. I don't think I'm going to use 4 because it's not going to show up on this grid. But let's take this number here, 2 and 3. Notice now I'm talking about x values, whereas before when I did vertical transformations or vertical stretches and shrinks, I was talking about the y values. So now I'm going to take these and I'm going to stretch them. Of course, 0 times 1/3 is still 0. So that's not going to change. This origin is going to stay put. But the 1 here will turn into a 3. So this 1 stretches out to that point. So we would get 3, 1. So for example, well, I'll get to that in a second. This value, this x value of 2, would stretch out to be 6. Okay? And then this value of 3 would stretch out to be 9, but I'm not going to go there. So check out this new graph. It's been stretched by a factor of 3. So t of 3 should be equal to f of 3 over 3, which is f of 1. Let's see if that's true. So f of x is the blue graph. T of x is the black graph. So t of 3, let's see what t of 3 is. Well, t of 3 comes out to be 1, and f of 1 comes out to be 1 as well. Okay, so it's true. All I've done is I've stretched that, I've kind of pulled it horizontally, and in that way I've reduced the y values in horizontally stretching it. Now m of x is a horizontal compression, so it's going to take all points and it's going to compress them toward the y-axis by a factor of 1/2. So it's going to take this point right here, which is 1, 1, and it's going to make it 1, 1/2. Okay, now I'm not going to do all of the sketching like I did on the last problem where I took a point and I translated it, because it won't make sense when you see the graph as a whole. But what it's going to do is it's going to take this right side and it's going to compress it in. It's going to take the left side and it's going to compress it in. So the new function will look kind of like this. So ignore the red function for a second. Okay. Here we go. Kind of like that. Okay, it's compressing everything in. And giving us this compressed stuff function. Of course, you can see how I mean, I guess I could work on trying to show you which points translate to which, but you might be able to see that. Okay, so this point obviously translates here. The closed circle that was there translates there. Okay, and all that good stuff. So again, we've compressed this by a factor of 1/2. So this point here that was at x equals 2 is now at x equals 1. This point here that was at x equals 3 is now at x equals 1.5. So we've compressed it by a factor of 1/2 coming from both directions. Okay, that is a horizontal shrink by a factor of 1/2. Got a couple slides left here. I'd like to go over a couple more problems. Hang with me, and then we'll have a nice night, and you can go out for a nice run and do some pull-ups or something. Those are the best body weight exercise there is. All right, let's keep moving. All right, I would prefer that you would maybe take this slide, pause the video, attempt these. I would also draw, if I were you, get used to drawing the parent function. You won't be required to draw the parent function on test unless told to do so, but it can sometimes help you to see the shape of the graph take form. So I'm going to draw the parent function on each of them. I'm going to pause the video real quick and do that, and I'll come back and explain from there. Okay, so I have sketched all the parent functions out here. I just like to highlight what they are. I got f of x equals x squared. You can see from the original function, we're going to do a vertical stretch. Then I've got f of x equals x cubed. We're going to do a horizontal stretch. The absolute value of x. Looks like we got a bonus reflection in there, but we're going to do a horizontal compression. Okay, excuse me, a horizontal stretch. This would be a horizontal, horizontal compression. That was my bad. And then we got a vertical compression or shrink. And then, of course, that's with e to the x. And then, of course, we've got the greatest integer function here. We're going to do a horizontal stretch by a factor of 2. So let's get started. I'm not going to get real particular right now about the points on the graph, but I am going to take this point here, which is 1, 1, and turn it into 1, 3. Oops, I didn't get that in the right place. Looks like I'm going 2. Okay, cool, got it. Boom, I got 3x squared. It's looking pretty good. There we go. So that would be the transformed vertical stretch of x squared turning into g of x, which is 3x squared. Okay, so h of x, I've got a horizontal stretch by a factor of 2. Of course, we see division, but we should always think opposite on the inside. So I'm going to stretch this value right here, which has an x value of 1 out to an x value of 2. And then I'm going to stretch this x value from -1 out here to -2. So our graph, and of course I'm not going to be way off. I'm not going to be all that accurate beyond those points, but I'm really not concerned about it. On a test, I might ask you to find those 3 points that are on the graph, or at least 3 points that are on the new graph. After the transformation, you would want to identify those 3 points. Of course, they would be -2, -1. It's kind of hard to see. 0, 0, and 2, 1. You could always confirm those by plugging them back into the function itself. Okay, let's take, v of x here and construct that. Okay, so I somehow figured out how to get purple on here, so that's great. So I'm going to do let's reflect it first. No, let's do the horizontal stretch first. Yeah, let's do that, and then we'll do the reflection. Okay, so we're going to reflect vertically after we do the horizontal stretch. Compression. So this right here is a 3, and at times it confuses me. Sometimes I forget, but on the inside we always do the opposite. So when I think 3 on the outside, that's a stretch, but on the inside, that's a shrink. So I'm going to take, let's see, what number is divisible by 3? How about 3? So here's the point 1, 2, 3, and I'm going to take that point, which is at 3, 3. And I'm going to compress it down. I'm not going to change the y value. I'm only going to change the x value. I'm going to shift that in and make that 1, 3. So that's a horizontal shrink. Of course, the point 0, 0 won't change. And then this point over here, since this is an even function, that will translate into that point. So what I'm going to have is I'm going to have an absolute value that looks like this. So that would be some function. I could call it w of x, which would be the absolute value of 3x. But I want to reflect that now vertically. Therefore, and I'm not going to fill in the points, but it would look something like that. The lower stem flipping that v over. Okay, awesome. Let's take a look at e to the x. E to the x has what I would consider 3 special points that you want to try to be aware of. Okay, when for an exponential function, this point right here, I'm strategically putting these coordinate pairs, ordered pairs, up above the function because we're about to compress it vertically, do a vertical shrink. But this point here would be 0, 1. This point here would be 1 comma e, right? That's e to the first. And then this point right here would be negative 1 comma 1 over e, because e to the negative first is 1 over e. So if I did a compression, I don't have brown on here, I'm going to use red. But if I did a vertical shrink by a factor of 1/10, I'm taking those values and dividing by 10, right? What I would get is 1/10 e over 10 and 1 over 10e. Okay, those values are going to get really small. Okay, so I'm going to try to squeeze this function, and that's not entirely accurate. I would likely not have you graph this for accuracy, but just to know that you see that it's going to be much closer to its horizontal asymptote here at y equals 0, and it's going to kind of maintain a distorted version of e to the x. Okay, so this point right here would be 1 comma e over 10. This point right here would be 0 comma 1/10. And this point right here, which of course not to scale, would be negative 1 comma 1 over 10e. That's a really small number. That's like 1/30th or about there. So that's how we would transform e to the x using a vertical shrink. Okay, let's look at the last one here, and then we'll get to the last slide. This is our greatest integer function. I only plotted it on the right side, but if I do, you would do the whole thing or whatever you're instructed to do. But if I did a horizontal, now notice here, we've got a horizontal stretch. So I'm going to stretch this out. Okay, I'm going to pause real quick and see if I can find an orange marker. Oh yeah, I found one. So if I stretch these x values, this x value is at 1, okay, this x value is at 2, this x value is at 3, etc. If I stretch them out, of course this one's at 0, so it's not going to change. But if I took this open circle at 1 and I doubled it, I would put it at 2. And if I took this closed circle at 1, 1, right, this one right here, and I doubled it, it would fill this in. And so on and so forth. And things would lead us to a graph that repeats itself half as often. Okay, so that's kind of weird wording, but it doubles the lengths of the steps if you do a horizontal stretch. Okay, it's pretty cool. Of course, I mean, you could verify this using algebra. If I took the number, I don't know, let's go 1.75, and I plugged it in here, so Q of 1.75. All right, let's find where 1.75 is, first of all. 1.75 would be kind of like right along this line here. Okay, so Q of 1.75 is equivalent to the greatest integer function of 1.75 over 2. What does the greatest integer function do? It takes a decimal value and it rounds it down to the nearest integer. So this would come out to be, oh boy, what would that be? About 0.875, I think. If I round that to the nearest integer beneath it, it would round down to 0. And that's why at 0.75, we've got an output of 0. Okay, so a little bit more there on the greatest integer function. Let's move to the last slide. Okay, I'd definitely like you to go ahead and pause the video and attempt to do what you can here on doing it looks like part 1 is a vertical stretch, part 2 is a horizontal shrink. Nope. Yep, horizontal shrink. And part 3 is a vertical shrink. So go ahead and graph what your new function would look like. All right, I'm going to go ahead and do the same, but I'm going to do it on camera. So if I took this and I multiplied all these values by 3, of course I'm going to multiply the y values, right, because it's a vertical stretch. So 0 times 3 is still 0. Negative 1 times 3 is negative 3. 1 times 3 over here is 3. And 2 times 3 is 6. Whoa, way up there. All right, so I'm going to have a graph that looks something like this. That's a goofy one. Okay, the second one. I'm doing a horizontal shrink. So now I'm going to use x values. And I want x values that are half of each of these. So half of 0 is 0, half of 1 is a half, half of 3 is 3 halves. I keep the same y values, nothing changes there. And half of 4 is 2. So my graph here for f of 2x should look kind of like that. That's a cool, good looking graph. Kind of looks like a lightning bolt. All right, for the last one, I'm going to multiply the y values by 1/4. Ooh, this is going to get kind of nasty. So 1/4 of negative 1 is negative 1/4. 1/4 of 0 is still 0. 1/4 of 1 is 1/4. And 1/4 of 2 is a half. So this graph is really cool, kind of a flat, yeah, really weird one. Compresses it vertically. It's like it's getting stomped from above and pushed up from below. Okay, guys, that's it for lesson 1D, part 2. I will have some practice with kind of putting all of these transformations together. I don't think I'll ever have you do 4 transformations at once on one function, but 2 to 3 is definitely possible. So have a great day. We'll see you in the next video.